Hello everyone. As announced in the previous class, I have an external event during the Monday's class, so I cannot have the real-time class for the Monday class. So I'm recording this video for the Monday class, and then I will post this video on the YouTube. So please watch this recorded video for the Monday class. So actually, today's class will include the very important topics regarding cash and then cash organizations. So please watch thoroughly this video. Okay, so in the previous class, we learned about the organization of cash. Actually, we learned about the organization of direct mapped cash. So as I explained, so we learned about the pipeline processor in chapter 4, and then I explained that actually this pipeline processor includes instruction memory and data memory, but these instruction memories and data memory are actually level 1 instruction cache and level 1 data cache respectively. So that means when the load instruction, for example, the load instruction is executed like this. So in this load instruction, this is the address of the data, and then the data is requested to the data memory. So that means the data is requested to level 1 data cache with the address. But I explained that cache memory is the temporary storage space. That means the cache size is much smaller than the actual size of the main memory, like the RAM. And then, but cache is much faster than the RAM. That's why the cache size is smaller. So cache has only small amount of data compared to our main memory, like the RAM. So the cache size is determined by the size of a single cache block. So cache memory looks like this, okay? And then the data is stored in the one single cache line or one single cache block. So the entire cache size is determined by the size of a single cache line, like width of the cache, and the number of entries in cache. So that means number of blocks in this cache. So the size of cache is the size of single block multiplied by number of blocks. Okay, then how can we store this data to the cache? So this is the cache memory. So that means the cache has multiple blocks that stores some specific amount of data. So the address for this cache is called the index. Okay, because we think like that the cache is some group of cache blocks. So actually the address to a certain block is called the index. So we can access a certain block in this cache with the index of the data, index of block. Okay, so how can you organize this address to the cache index and then offset and then tag of the cache? So this figure shows the example organization of the direct mapped cache, and as you can see, this cache includes 1024 entries, and then the size of single block is it's 4 byte. Okay, so that means that the 4 byte of data is stored in a single cache block. So this byte offset is assigned to the a single block because the single block includes the 4 byte of data. And then you need to remember that in the modern processor, the address is byte address. So that means that the address number 1 occupies the 1 byte of data. So, and then this cache, a single cache block includes the 4 byte, that is the equivalent to 1 word. So these 2 bits are assigned to the byte offset, okay? And then the next 10 bits are assigned to the index of the cache. And then this is the direct mapped cache. So this lower part of address is assigned to the index of the cache. So that means, and the address, so this, let us assume that this address for data is the 00000. So in this case, we just check the index number 0 for this direct mapped cache. Then how can we know the requested data exists in the cache? So this is the direct mapped cache, and then I explained that in order to identify the request data in this cache, we need to store address of the target data. But this is direct mapped cache, so we can use this part as the index of the cache. So we don't need to store this part because we already know this part with the index number for this cache. So we just store remaining part, and this remaining part is called tag. So this is the organization of a single cache block. A single cache block includes the cache flag, or this, and then this cache only has the valid bit. The valid bit indicates that the corresponding cache block includes a valid data or not. And then also we need to store the tag to identify the stored data in this block. And then data is stored. What is the size of the data? The size of data is 4 byte because the byte offset is 2 bits. Okay. And then this is tag. And as you can see, the tag includes the bin number 63 to bin number 12 of the address field. And then also this cache includes the valid bit. And then one student asked after the class, and then when we mention about some size of the cache, we just consider the size of the data field. So the size of this cache is, so size of a single block is 4 byte. So it's the data size. And then this cache includes the 1024 entries. So the size of this cache is 4 byte multiplied by 1024. It's 4 kilobyte. Okay. And then also we discuss the effect of large block size. So if we use the large block, then we can exploit the spatial locality of applications. That's a spatial locality of data. So that means the one request is given to the cache, and if this request is missed, then cache fills the entire block. That means the single block. Okay, so that means if the cache line size is 4 byte, and then if cache miss happens, the cache request 4 byte of data to the low-level cache or memory. And then let us assume that the cache size is 16 byte. So in this case, when cache miss happens, this cache requests 16 byte of data to the low-level cache or data memory. So the size of a single cache line determines the size of request data when cache miss happens. Okay, and then if the size is large, then when this block is this data is missed, then an additional data is stored in the cache. So in this case, even though this block is missed, then in a near future, then with a high probability, an application may request the neighbor data. In this case, if the cache block size is large, then the neighbor data is already exist in the cache. So then the cache can provide the request data from this large block. Okay, but this is the advantage of the large block size of the cache. But what is the disadvantage? Is the large miss penalty. So I explained that when cache miss happens, the cache requests the same size of data to so the the data and then each amount of data is same to the size of a single cache, size of a single block. So this amount of data is requested to the low-level cache. So that means if the size of a single cache block is 16 byte, then cache need to request the 16 byte of data to the low-level cache. Then if a 4 byte, then cache requests the 4 byte of data to the low-level cache. So if this request data size is increased, then the low-level cache will consume more cycles to provide the larger amount of data to the higher level of cache. Okay, so if the block size is large, then the miss penalty is also increased. Then this is the disadvantage of the large cache block. And then in this class, we will learn about some performance factors of the cache organization. So then I believe you can understand why this miss penalty is critical for the performance of cache. Okay. Okay. So and then I also explained how the processor works for the miss cases. And then now we will learn how the write operation is handled in the cache. So what is the write operation? So it's store operation, like store word. Oops. I will change the, oops, what happened? I check the, doesn't work. Okay. Okay, it is working. Okay. So what is the write operation to the cache? So if the store instruction is executed in the pipeline processor or any processor, then the write operation is requested to the cache. So what is the write operation? So this is the cache, and then a certain data is stored in this cache, and then write operation is performed by processors like store word x1, x0, x2. So this is the address. Okay. So, but we learned that the cache line size may be larger than the size of data handled by an instruction. So, for example, in this example, the processor executes the store word instruction, but the size of a single cache line may be larger than this single word, like maybe 16 word. So what will happen for this case? When this store instruction is executed, then let us assume that this block is already stored in the cache, but this cache line size is larger than a single word. So when this store instruction is executed, only part of data in this single cache line is updated. So for example, only the part of data, like this data, is only updated in this cache. So what's the problem? Cache is the temporary storage space. So actually, when this store instruction is executed, we assume that the data is stored, updated in the main memory, right? So in chapter 2, we learned that when an instruction is executed, the data in register file or main memory are updated. So I explained that. That means the state of the computer system is updated or updated by instruction. But so actually the definition of the store instruction is that when the store instruction is executed, the data in main memory is updated. So that is the definition. But why do you use cache? The main memory is so slow, so we temporarily store the frequently used data inside of the cache. And then when the store instruction is executed, then the cache is firstly accessed by processor, and then the store instruction will update the contents of the cache, okay? Then what should we do for this write operation? So there are two kinds of how handle the write operation by this cache and main memory. And then the first handling method is the write through, and then the second, the write handling method is the write back. Okay, so let's see what is the write through or what is the write back. Oh, why the figure is erased. So this is the cache. This is main memory, and then this is the some cache line, and then we store some data to cache with the address of this store instruction. So, and then I said a part of data can be updated to the target cache block, and then this is the some another the address space of the main memory. So write through means that when the write is performed to the cache, and then this updated to the cache is immediately updated to the main memory also. So that means on data write hit, so data write hit means that the store instruction is performed by processor, and then this store instruction updates the a certain cache block in of the data cache. So this is the write hit because this data exists in the cache. So this cache block is updated, and then by the write through method, when a certain cache block is updated by store instruction, and then this block is sent to the main memory. So that means that the same data in this main memory is also updated. This is the write through method for write handling. So for the write through, so also update the memory. So with this write through, the data in this cache and then data in this main memory is identical for the write operation, right? Because when the write operation is performed to the cache, and then this update is immediately update transferred to the main memory, and then the main content of the main memory is also updated. So that means that the data of the same address has the same value in this cache and main memory. And actually this is very important, okay? So, but what is the disadvantage of a write-through method? Okay. So I mentioned that why do you use cache? Because the cache is fast. Cache is much faster than the main memory. But with the write-through method, when the cache content is updated, then this updated cache block is sent to the main memory, and then that means the main memory should be accessed for this request. So this write request from cache. So that means whenever the store instruction is executed by processor, then the main memory is accessed by this store instruction. But you need to remember that the main memory is so slow. So with this write-through method, then the performance can be degraded. Okay, that is the disadvantage of the write-through method. What's the problem? Okay. So this is the example. So if this is the base CPI, and then let us assume that 10% of instructions are stored, and then the write to memory, let us assume that the write to memory takes 100 cycles. So what is the effective CPI? This is the base CPI, and this is the increase the CPI by store instruction. So the percentage of store instruction is just 10%, but the penalty by this store instruction is 100 cycle. So the effective CPI is 11. So with this write-through method, the performance of CPU is degraded by 11 times. It's very huge. So how can you solve this performance degradation by write-through method? We can use the write buffer. So write buffer means that instead of directly access main memory by cache from cache, so erase this path, then so this is the fast component, and this is the slow component. In this case, instead of directly access main memory with the write request, we can add the buffer. And then this buffer is called the write buffer. So that means that when the write request is sent to the main memory, these write requests are temporarily stored in this write buffer. And then this write request is stored in this write buffer, and then cache can do other things, other operations. So processor does not need to until the write operation is done in the main memory. This write request is also stored in the write buffer, and then the cache can do other requests. So this is the write buffer. Okay, the another method is the write back. So write back means that, so this is the cache, and this is main memory, which is very large. This is cache, and then this is the main memory. And then when the store instruction is executed by a processor, then a certain cache block is updated by this store instruction. With the write-through method, when this cache block is updated, then this update is immediately reflected to the main memory. That is the write-through, but write-back is different. So write-back means that, oh, this cache line is updated by store instruction, but this update is not immediately sent to the main memory. So what does that mean? This update is just stored in the cache. And then also you can expect that the same cache line is updated by other store instructions. So that's right, because the data of an application will exhibit data spatial locality, and it's the same to the store instruction. So with the another store instruction, the cache line can, another part of the cache line can be updated, and then with the another store instruction, another part of the same cache line can be updated. So this update to the cache line is just stored in the cache. And then when these updates are reflected to the main memory. So cache is the temporary space, a temporary storage space, and the cache size is small. And then in the previous class, we learned that the cache block can be evicted from the cache. Which situation? The cache is all occupied by previous data, and then this cache should be updated by new data. In this case, this old data is evicted from the cache. So because the cache size is small, the cache data can be evicted from the cache. So with the write-back method, this updated cache line is reflected to the main memory when the corresponding cache line is evicted from the cache. Okay, so when this cache line is evicted from the cache, then this updated data can be erased, so can be removed from the computer system. So in this case, this updated cache line is sent to the main memory, and then the main memory is updated. This is the write-back method. So in order to implement the write-back method, we need to mark that if this cache line is updated or not. Okay, so this flag is called the dirty bit. So we learned about the valid bit for the cache line, and then also this is the another flag for the cache line. So dirty bit means that if this cache line is updated by store instruction, then dirty bit becomes the 1. And if not, and that means the cache line is not updated after this cache block is allocated to cache. So that means the data of this cache block is identical to the data of the main memory. So in this case, the dirty bit becomes the 0. So this is the clean state. So okay. So when is dirty bit 0? When the cache when cache miss happens, then this cache will request data to the lower level cache or memory. So that means this cache block is newly allocated to the cache. Okay. So in this case, this data is identical to the data in the low level cache or main memory. Okay. So in this case, the dot bit becomes the 0. But if this cache line is updated by new data by this store instruction, then this cache line, the dirty bit of this cache line becomes 1. So dirty bit indicates that if this cache line is updated after allocation. Okay. So if the dirty bit is 1, and if this cache, when this cache line is evicted from the cache, this cache line should be updated to the main memory. This is the write back method. Okay. So what is the advantage of the write back method? So even though the multiple store instructions are executed, and then the cache lines are repeatedly updated by these store instructions, then we can reduce the number of write requests to main memory. When those when each write request sent to the main memory, and the dirty cache line is evicted from the cache. Okay. So this cache line is written back to the main memory when this cache line is dirty. Okay. And then what is the problem? So problem is that the data in this cache may be different from the data in main memory, and that's obvious. When this cache line is updated, but the main memory is not updated immediately. So the data can be different in this cache and the main memory. So what's the problem? Actually, the address for this data and main memory are the same, right? With this store instruction, then we assume that with this store instruction, when this store instruction is executed, then programmer, the software assume that the data in the main memories are also updated. But it's not true in the write back cache. In the write back cache, and the store instruction is just executed, then the contents in the cache is updated, but this update is delayed until this cache line is evicted from the cache. So that means it's the same data, because this data in this cache has the same address to the data in this main memory, but the value of the data can be different by write back cache. Okay. This is very tricky operation by write back cache, and then it's so in the multi-core system, this operation may be very complex. So we may, with the multi-core system, then we need to handle this situation. Okay, but it's some out of scope of this course. So if you take the advanced computer architecture course, then you will learn about this issue. Okay, and then also another write related operation is the write allocation. So write allocation means that. So until now, so we just learned about some cache operation by read miss. So what is the read miss? So root instruction is executed by processor. And then when this load instruction is executed, then the read request is given to the cache. And then when this request is missed in the cache, then what will happen? Then data for this corresponding cache line is requested to the low-level cache or main memory. So this is the read-miss operation. And how about the write-miss? So what is the write-miss? It's the same. Oops. So erase does not work. The store instruction is executed, but when this store instruction is executed, the target data is not found in the cache. This is the write-miss. So when I explain about the write-through or write-back cache, then our assumption is that this is the write-hit case. So that means that when the store instruction is executed, then the request block is found in the cache. Okay, this is the write-hit case. But I am explaining about the write-miss case. So write-miss case means that the store instruction is executed, but this target block or target data is not found in the cache. So what should we do in this case? There are two different approaches for this write-miss. The first approach is allocate on miss, and then the second operation is write around. So allocate on miss means that, so this operation for allocate on miss is same to the read miss case. So what does that mean? So how does cache handle read miss case? What is the read miss? So when the load instruction is executed, then this target data is not found in the cache. So this is the read miss. Then the cache requests the data for this target cache block to the low-level cache. This is the read miss case, read miss handling by cache. Allocate on miss is the same. So allocate on miss means that if a write miss happens, then this target data is not found in the cache. Then cache requests the data for the corresponding cache block to the low-level cache. This is the allocate on miss. So in this case, the cache fills the target cache block with the data provided by low-level cache and then updated. So this is the clean case, clean state. And then the store instruction is executed. So the part of cached data is updated. Okay, this is the allocate on miss case. And the write around means that this is just the store instruction. So we don't need to read data from the cache. So this is this direction. So this update to the main memory or low-level cache. So write around means that don't fetch the block. So don't request data to the low-level cache. Just bypass this store request to the low-level cache or main memory. Okay. So this is the write around operation. And then for the write back cache, we usually applies the allocate on miss handling. Okay. So actually for the modern processor, so most of the processor use the write back policy for the write operation. And then so that means we frequently use the allocate on miss for the write miss. Okay. we frequently use the write back cache, and then that means we also use the allocate on miss for the cache. Why that doesn't work? The save doesn't work. Okay. So let's see another example of the cache organization. So this is the cache of the interesting fast math processor. This cache has the 16 kilobyte of the cache, and then that means this cache includes the 256 cache blocks, and then the size of a single cache block is the 16 words. Okay, so one word is the 4 byte, and then this is the block size. So what is the block size of this cache? 16 multiplied by 4 is the 64 byte. So let's see how this cache is organized in this processor. So as you can see, the cache size is the 16 kilobyte. Now, how many entries in this cache? The number of entries in this cache is 256 blocks. So, and then let us assume that this is the direct mapped cache. Then what is the size of index field? So number of entries in this cache is the 256. Then the size of index field is 8 bit, right? And then what is the size of the block? The size of a block is the 64 byte. So that means the block offset is 6 bit. So because it's the 2 to 6, this is the 2 to 8, 256. So how can we assign the index, tag, and block offset for this cache? The block offset is 6 bit, and then index field is the 8 bit, and the remaining bits are used as the tag. Okay, so this is the organization of this cache, and then as you can see, this is the address field, and then actually we are learning about the 64-bit processor, but this interesting fast math processor is the very old processor. So this address field is the 32 bits, and then as you can see, this is the size of the index field, and then remaining part is the size of the tag field. This is the tag, this is the index. And then, why is it erased? So this part is the block offset. But in this example, so we assume that the block is composed of 16 words. So this is the byte offset for one word, and then this is the block offset. So this is 4-bit, and then this is 2-bit, and this is the 60-bit, so block offset. So how can you handle this cache? So this cache is accessed by index field, and then this block includes the 16 words, and then let us assume that this processor just access the word sized data. Okay, so as this block includes the 16 words, and then the load word instruction, when the load word instruction is executed by processor, then we need to select the one word from the entire cache line with this block offset. So there are 16 words, and then we need to select one word from these 16 words. How? We can use the block offset. So we can use the 16 to 1 mux, and we use this 4-bit block offset as the selection signals for these mocks. Okay. Okay. And then let's discuss about the cache performance. So in the chapter 4, so these slides explain about the influences from the main memory, and then this slide just assume that this is the cache, and the cache is just connected to the main memory. So it's the main memory and the cache. And then this slide just explain how the cache penalty is explained, but we will learn about the cache penalty, the miss penalty in the this following slide. Okay. Okay. In chapter 4, we learned about the pipeline processor. Sorry. So in the pipeline processor, but we just assume that in this pipeline processor, when the load instruction is executed, and then this processor just access the data memory, but we assume that this data memory can be accessed within 1 clock. But we learned that this data memory is actually data cache. And then because this is the cache, we have the 2 possible cases. So hit case and miss cases. Okay. So in chapter 4, we just assume that when the cache is accessed, every access is hit. So when the cache is accessed by load instruction, then we assume that this data memory access can be completed within 1 clock. Okay, we just assume that every access for this cache is hit. But in this chapter 5, we are learning about memory hierarchy, and we already learned that when the cache is accessed, there are 2 cases, 2 possible cases: cache hit and cache misses. So we need to also consider these miss cases. So when in the chapter 4, when we calculate the performance of this pipeline processor, so that means that we can calculate the performance of a pipeline processor with CPI, clock per instructions. So usually in a pipeline processor, it's a very simple pipeline processor. So we assume that if there are no hazard, then CPI for this pipeline processor is 1. And then we assume that for this case, we assume that the cache is always hit. So that means CPI equal 1 is an ideal case. That means, and this assume that this is the only hit cases. Then if we just consider the more realistic memory systems or memory hierarchy for this processor architecture, then we need to consider the memory store cycles. That means that it's the miss cases, cache misses. Okay. So what is the memory store cycles? When cache miss happens, then the pipeline processor needs to wait until the requested data is fetched from the main memory or low-level cache. So it should be stalled. So when the pipeline processor is stalled, then cycles are wasted. So we need to calculate these wasted cycles by memory operations. So these wasted cycles by memory operations are called the memory store cycles. And then how can you calculate these memory store cycles? So memory store cycles are caused by cache misses. So we can calculate the wasted cycles by cache misses like this. This is the memory store cycles are equal to memory accesses per program. So this is the number of memory accesses in a program. So this is the total memory accesses of a program and multiplied by miss rate. So for the hit case, the cycle is not wasted, but when the miss happens in the cache, then the cycles are wasted. How many cycles is the miss penalty? It's the cycles wasted by cache misses. By it means the cycles wasted by a cache miss is the miss penalty. So miss rate multiply miss penalty is the wasted cycles by cache miss, and then is multiplied by number of memory accesses in a program. We can rewrite this equation with the number of instructions in a program. What is this? This is instruction count multiplied by number of misses per instruction. So it's a number of misses per instruction and then multiplied by miss penalty. Okay, so this is the equation for memory store cycles by cache misses. Okay, let's see the example. So in this example, I cache miss rate is the 2% and the D cache miss rate is the 4%. I cache means the instruction cache and then D cache means data cache. And then this is the miss penalty. So that is the wasted cycles by cache miss. So it's 100 cycles. This is the base CPI. So that means that for the ideal case, which means every access to cache is hit. So base CPI is 2, and then load and stores are the 36% of instructions. So let's calculate the wasted cycles by cache misses. So there are two kinds of cache for this processor. So instruction cache and then data cache. So instruction caches are accessed by every instruction. Okay, because the instructions are stored in this instruction cache like instruction memory. So instruction cache is accessed by every instruction. So how can you calculate the wasted cycles by instruction cache misses? It's a 2% and the miss penalty is 100. So wasted cycles are 2 cycles. How about the data cache? Data cache is only accessed by memory instructions like store and load instructions. So the percentage of store and load instructions is 36% of total instructions. So we need to use this fraction for memory instruction, 0.36. And then this is the miss rate for the data cache. So 0.04, and then this is miss penalty. So wasted cycles by data cache misses is 1.44. So this is the base CPI, and this is the wasted cycles by instruction cache misses, and then this is the wasted cycles by data cache misses. So total CPI is 5.44. So if we just compare the performance with the ideal CPU, then this, when the cache miss is considered, then this processor is 2.72 times slower. That means the ideal CPU is 2.72 times faster than the real CPU. So that means that the cache misses, when the cache misses are considered, okay? So it's very, very slow, okay? It's just cache miss rate is just 2% or 4%, okay? But the processor performance can be significantly degraded by small fractions of cache misses, okay? And then also we can calculate the average access time. So what is the average access time? So this is the memory, right? So cache. And then when the instruction is executed by processor, then instruction cache or data cache can be accessed by this processor. So, but there are two possible cases for this cache accesses, like hit and miss case. Hit cases and miss case. We already learned that for the hit case, the clock cycles are not wasted, but for the miss, the clock cycles are wasted. So average. So actually we assume that this level on cache, the access latency for level on cache is less than the clock cycle. So that means that is actually hit time, hit access time. When miss happens to this cache, then we need to add more cycles to handle missed request. Okay. So average memory access time in abbreviation form, it is called AMAT. Okay. So average memory access time is called AMAT, and this AMAT is calculated like this. It's the hit time, so it's the access time for hit cases, and then miss rate multiplied by miss penalty. Okay. So average memory access time includes the access time increased by missed request. Okay. So this is the equation for the average memory, average AMAT, average memory access time. So it's a hit time plus its rate multiply miss penalty. So it's this example, the CPU clock cycle period is 1 nanosecond and the hit time is 1 cycle. So actually when cache is hit, then the cycle is not wasted and the miss penalty is 20 cycles. The cache miss rate is 5% for the instruction cache. What is the AMAT? The hit time is the 1 cycle plus 0. Is a miss rate is the 5% and then miss penalty. So it's the 2 nanosecond. So it's same to the 2 cycles per instruction. Okay, because of cache miss, the average memory access time is longer than the hit access time. Okay. Okay. Let's summarize the performance factors by cache memories. So, so you can think like this. So this is the processor or core, the processor, and then there is the memories or memory systems, and then usually the processor is faster than memories. Okay, so That means the clock frequency for processor is higher than the clock frequency for memory devices. So, but in a previous slide, we learned that the memory store cycles are determined by this miss penalty, miss rate, and number of memory accesses in a program. Okay, so if if even though we can increase the performance of a CPU like a processor, and then but if the performance of a memory system is the same, it's just maintained, then this penalty becomes more significant. And then actually that's obvious. What is the miss penalty? Miss penalty means the required cycles to transfer request data from the low level cache or memory. But let's also the clock cycle, the clock frequency of the processor is increased. So that means the clock frequency becomes faster. So that means the miss penalty will be also increased if the performance of memory system is the same. Obvious, right? So in this case, the miss penalty is increased, which means the wasted clock cycles by this cache misses will be also increased. So it will occupy a significant fractions of total performance of computer systems. Okay. So actually these sentences or these items all increase the same aspect of the memory systems. And okay, so what is important? Memory system, the performance of a memory system is very significant, very critical for the entire performance of computer systems. Okay, it will dominate, even though the CPU frequency is increased. If we do not increase the performance of memory systems, then the overall performance of the computer system may be slightly increased. Okay, very slightly increased, because the performance of a memory system is very critical. Okay, you need to remember. Okay. Okay. Then this is another topic of the cache organization. So let's learn about the associativity of cache. Okay. Okay. In the previous class, we learned about the direct mapped cache. So what is the direct mapped cache? Actually, in the direct mapped cache, the lower part of the address just determines the index of the cache block, and then based on this index field, the cache has only one cache block. That is the direct mapped cache. And then what is the disadvantage of direct mapped cache? So disadvantage means that the disadvantage of direct cache is, what's that? If the cache index is the same, and then this cache index can only store one cache block. What does that mean? So let us assume that this is the address. Two. And then let us assume that this is the request by load instruction with a 04, 08, and then 12. And then let us assume that this request have the same index number to the direct mapped cache. What's the problem? So, and then it's the sequence of the request, and the same index. These addresses have the same index numbers. What's the problem? So it's a miss. What's the problem is that cache has enough space, so that means that enough number of cache blocks, but these access sequences have the same index numbers. These data just stored to the same cache location, the same cache block. So even though the cache has many other cache blocks, only the same block is stored, used for storing the request data. So the cache space is wasted. So this is very some what's that? So for the direct method cache, the one index is only stored the one cache block, and then if the the request sequences have the same cache indexes, then this is allocated and then evicted, and the new cache block is allocated and evicted. But as you can see, these sequences have the locality like what's the problem? The locality, that means that with this sequence, 04 is repeatedly accessed, 08 is also repeatedly accessed, 12 is also repeatedly accessed. So that means this application, this data has temporal locality, but this locality is not utilized by cache. Why? These sequences share the same index number. So, and then so one index number can store only one cache block. What's the problem? Well, it's stored and then evicted by this access, this request, also stored this data, and then also this allocated cache block is evicted by this request 12, and then 04 is repeated, re-referenced again, but this data is not found in the cache. Why? This block is evicted by previous request that shares the same index number. That is the disadvantage of direct mapped cache. Then, how can you solve this problem? So I explained that we can just identify the data with the address. Okay. So if we just remove this rule, so then what's the rule? So, this is the index field of the cache. So it's the address, but the low part of the address is used as the index field. But if we just remove this rule, and then if we just store the entire address for the data, then we can identify, then we can store this data to any blocks of cache. Okay. So that means given block to any cache entry. So we just ignore the index field. We just ignore the index field and then store any request data to the any entry location inside of cache. That's possible if we just store the entire address of the data, right? And if we can just check the entire entries to identify request data, then we can find the target data in this cache, okay? Then this cache is called the fully associative cache. So fully associative cache means that we just ignore the index field and then store a certain cache block to the any entries of cache. And then we just store entire address as the tag of the cache. Okay, then we can identify the data inside of the cache. And then in order to access the data in the cache, we need to, what the problem is that we need to compare the entire blocks, the tag of entire blocks for the fully associative cache. So with the fully associative cache, we can reduce the wasted cache blocks by direct mapped cache. But problem is that we need to, in order to identify the cache request data, then we need to compare tags of entire entries in this cache. Okay, it's very expensive. We need the comparators for all cache lines. So another solution is the n-way set associative cache. So n-way set associative cache means that one cache index may include n cache blocks. So in the direct method cache, one cache index can include only one cache block. It's direct method cache. But n-way set associative cache is different. So with the n-way set associative cache, one index can include n blocks, the n block, multiple blocks. Okay. So these multiple blocks indexed by this single index field is called a set. Okay. So with the n-way set associative cache, one set can store multiple blocks, like n blocks. And then this set is indexed by set index. Okay. So for this NA set associative cache, this set index is the part of the also lower part of address, but one set can include the multiple blocks. So we need the n comparator to compare the tags of these multiple blocks in a single set. So this is the NA set associative cache. So NA set associative cache is less expensive than fully associative cache because we just need the n comparators. And then, but also we also say we also with this NA set associative cache, one set can store multiple blocks, so we can avoid this case. Like, so it's a repeated sequence, but the request shares the same index, but because of this sequence, even though this address is repeatedly referenced, but that is evicted from the cache. This is the disadvantage of the direct mapped cache. But with the set associated cache, we can store up to n blocks to the same set. So we can avoid this case. We can fully avoid this case with the fully associative cache, but fully associative cache is expensive because we need the number of comparators which is equivalent to the number of cache entries. Okay. So actually we can say that the direct mapped cache is one-way set associative cache because one set has only one cache block. So and then this is the organization of the two-way set associative cache. So in one set there are two cache blocks, and the four-way set associative that in one set there are four cache blocks. So this example shows that the cache has total 8 entries. So with the one-way set associative cache, that means the direct mapped cache, this direct mapped cache has 8 sets, and then each set has only one block. How about the two-way set associative cache? So this cache has total 8 entries, but with the two-way set associative cache, there are 2 blocks per set, and so there are 4 sets. Okay, so it's 8 entries. How about the four-way set associative cache? That means 4 blocks per set, so there are total 2 sets. Okay, how about 8-way set associative cache? This is equivalent to the fully associative cache because there are 8 blocks per set, and then because one set includes the 8 blocks, that means this 8-way set associative cache has only one set. Okay, so direct mapped cache is here, so it's a one-way, and then this is the n-way set associative cache. It's an n-way, and then the fully associative cache is the extreme case. So let's see the example of the cache associativity. So in this example, we just compare the operation of the cache for the direct mapped cache, and then two-way set associative cache, and then fully associative cache. And then let us assume that the cache has only 4 blocks, so 4 entries actually. And then this is the block address of the cache is 08068. Okay. So let's see that this. So this the 4 block means that the cache has only has 4 entries. Okay. So let's see the example of the direct mapped cache. So this is the block address 08068, and then because this is the block address, the cache and then this cache has only 4 blocks. So what is the size of the index field? The size of the index field is 2 bit because there are 4 entries for the direct mapped cache. Okay. So totally 4 sets. Actually, 1 block per set. So for the block address 0, the cache index is 0 because it's a 0, 0, 0, 0. So it's a 0. And then for the 8 is a 1, 0, 0, 0. So it's the cache index is 0, 0, 0. 6, what is 6? 6 is the 0, 1, 1, 0. So cache index is 1, 0. It's a 2, 8, 0. And then what's the operation of the cache? It's a miss because this cache index 0 is initially the cache does not have any data. So it's a miss here. And then when the block address 8 is requested to the cache, the result is also miss, right? Because it's a new data. 0 is accessed, but it's also miss. Why? This block, the memory 0, block address 0 is evicted from the cache. Why? By this request. So because 080 has the share the same cache index number 000, so this data is evicted from the cache. So we can know that, oh, there is the temporal locality here, but this temporal locality is not exploited by direct method cache in this example. Okay, so means 6. The 6 is assigned to the different cache entries, like entry number 2. So it's here. So it's, and then A is also accessed. It's also miss. Why? This data is evicted by this request. Okay, it's direct. So all requests are missed in this direct mapped cache. How about the two-way set associative cache? With this two-way set associative cache, one set includes the 2 blocks. So 2 blocks per set. And then there are total 4 entries. Okay, so it means this cache has the 2 set. What does that mean? The set index has only 1 bit. So in this direct method cache example, the set index has 2 bits. Okay, so cache. So this is the 0000100. So, but only this last bit is the index bit for this two-way set associative cache. So what is different? So cache index for this two-way set associative cache is the all zeros. What's the problem? What is different? So for the memory 0, this is stored in the set 0, and then for this memory request, is the block address 8, but the cache index is the same. When this request is given to the cache, it's a miss because this data is not found in the cache, but new data is allocated to the empty block of the same set 8. Understand? And then 0, oh, in this case, this block address 0 is not evicted in the cache, right? Because new block is assigned to the empty block of the same set. So, oh, this block address 0 is found in the cache. Hit 6. Oh, the cache index is the same, but oh, the target cache set has all valid blocks. So we need to evict one of these valid blocks. So in this case, the memory 0 is recently accessed. So we usually this cache evict the old data, the least recently accessed data. So in this case, this data is evicted from the cache, and then memory 6 is assigned to the cache set number 0. 8, oh, this data is evicted, so this data is not found in the cache, so it's a miss. What is different? So in this it's the same cache sequence, cache access sequences, but for the direct map cache, the 8 requests are all misses, but the 2A set associative cache, we have 1 hit. And then let's say the fully associative cache. Fully associative cache has no index field. Okay, so it's a block order 0. So it's an empty space. So assigned to the here 8 empty space. There are 3 empty entries. So 8 is assigned to here. 0 is a hit because it's found here. 6. There are 2 empty entries here. This block address 6 can be assigned to the one of 2 empty entries. Okay, here. So in the 8 is it's a hit. So in this case, with the fully associated cache, the 2 among 5 requests, 2 requests are hit. Okay, 2 hit. So if the hit rate is high, then that means the cache performance is also high. So usually the fully associative cache exhibit the highest performance compared to the NA set associative cache or direct mapped cache. So this is some real benchmark result. So it's the cache size is the 64 kilobyte in the data cache, and then the size of the a single cache line is the 16 words. And then with the 1A set associative cache, this is the direct mapped cache. The miss rate is 10.3%. The 2A set associative cache is the 8.6. 4A, 8.3, 8A, 8.1% miss rate. So actually we know that a fully associated cache is the best cache. So that means that with the fully associative cache exhibit the best performance. But as you can see here, if we just compare the hit rate or hit rate, then this hit rate is saturated by number of associativities in the cache. So as you can see, between this direct mapped cache to the 2A set associative cache, the miss rate is about 2%, so 1.7% different. But between the 2A and 4A, the difference of the miss rate is just 0.3%. 4A to 8A is about 0.2%. So actually the hit rate is saturated by this set associativity of the cache. So we already know that our fully associative cache exhibit the best performance, but we don't need to use the fully associative cache because it's expensive. But the performance is saturated by associativity of the cache. Okay. So this figure shows the example of organization of the set associative cache. So how many sets? In this cache, there are 256 sets. And then how many blocks in a single set? There are there are 4 blocks per set. So what is the set associativity of this cache? This is 4-way set associativity cache. Okay. So in this example, there are 256 sets. So the size of index field is 8 bits. Okay, it's 2 to 8. And then this is the byte of set. So that means the size of one cache block is 4 byte. It's 1 word. And then, so remaining bits are used as the tag. And what is the size of this cache? There are 256 sets multiplied by, and then one set includes the 4 blocks. 4 block multiplied by size of a single block is 4 byte. Here, it's 4 kilobyte. Okay, so how can this cache is accessed? With this index field, the cache set is accessed. Okay, so when this cache set is accessed, there are 4 blocks. So we can read the 4 different block data from this cache set, the target cache set. So, and then each block has the valid bit and tag. So we just compared this tag with this tag field of the requested address, and then compare, and then identify the request data exists in the cache. Okay, and then this is if the request data exists in the one of cache block in a target set, then it becomes the hit. Okay, so this is the organization of the set associative cache. And then because there are multiple blocks in a target set, then we can also determine which block will be replaced, which block will be rejected if the target set is already occupied by valid blocks. Okay, so what does that mean? The target set may have multiple blocks, and then these blocks are fully occupied by valid data. And then cache miss happens for this target set. So that means new blocks should be assigned to this target set, which means one of the blocks in this target set should be evicted. So which block will be evicted? This is called the replacement policy of cache. Okay? Replacement policy of cache determines which block should be evicted in a target set. With the direct method cache, there are only one block for in a set, so we do not have any choice. This block is evicted. But for the set associative cache, there are multiple blocks, and we need to select from these multiple blocks. Okay, so we usually use this least recently used policy. This is called the LRU. This is very popular policy. The least recently used means that we just select the least recently accessed. So which means if this block is not accessed for a very long time, so for the longest time, then the block is evicted from the cache. This is the least recently used. Okay, but it's a this LRU policy is simple for two-way, and then it's also implementable for the four-way, but it's very complex for the 8-way or some fully associative cache. So we can use the another replacement policy like the random policies. Okay, but we frequently use this LRU policy for the replacement policy. Okay. Okay. So I cannot check how many times. Okay, so I'll stop here. So I cannot check how long I. So I'll stop here. So in today's class, I explain about the right policies on the cache, and then how the cache. And then also I also explain the set associativity in the cache. Okay. So if you have any, so please watch this recorded video, and then if you have any questions, post your question on the Piazza. Okay. Thank you for your attention. Then see you in the next class. Bye.